Alright, welcome back to the last part of this lecture about humidity. Before we talk about other ways to describe the amount of water vapor that's in the air, we're already a little bit overwhelmed. We're a little bit saturated with ways to describe. Let's talk about how we would actually measure this. In practice, most measurements of humidity that would happen like in a National Weather Service observation or something like that, or like if you're in the ATS 114 lab, the observations that you'll see in your lab come from a piece of equipment called a Sling psychrometer. And this hand over here is holding a Sling psychrometer. It is two thermometers attached to a stick. I used to have one around my office, but I can't find it today. And you swing it around like this, and the thing goes round and around. There's two thermometers. One is a perfectly normal thermometer, exactly what you're picturing. It's got a bulb of mercury or alcohol or something down there. And all that's doing is it's just measuring the temperature of the air. We call that the dry bulb. The bulb is the little part down there that's holding the mercury or the alcohol or whatever. So that's the dry bulb thermometer. It's just measuring the air temperature. The one that's interesting is the one that's kind of wrapped up in a little piece of cotton, as you can see in that picture right there. That little piece of cotton is sort of a little sock. Meteorologists tend to call it a footie, like baby pajamas have footies. And you get it wet before you start to swing the thing around. And as you swing the thing around, it has evaporation happening on it. And remember, because, water vapor evaporates off of the little wet footie, which is a cooling process. And so the wet bulb temperature, which is abbreviated TW, is a temperature that will always be lower than the air temperature because there's always some evaporation going on, I suppose, unless there's saturation or something. And that wet bulb temperature tells us something important about the amount of water vapor that's in the air. And again, if you're in the ATS 114 lab, you're going to do this, okay? You're going to have some lab activity where you spin this thing around, and you can't just do it once or twice and then look at it. You have to spin it for like 2 to 3 minutes or something before it cools as much as it's going to cool. Now, if the air is dry around you, there's going to be a lot of evaporation happening off that wet bulb, and there will be lots of cooling, and so there will be a big difference between the wet bulb temperature and the regular air temperature, T, the dry bulb temperature. On the other hand, if the air is quite humid around you, there won't actually be all that much evaporation happening off of that little footie right there, so the little wet bulb, the little footie won't cool all that much, which means that the wet bulb temperature won't really be all that much different than the dry bulb temperature, T. This idea of having two temperatures there, the wet bulb temperature and the dry bulb temperature, is useful. Neither of those are the dew point. Dew is not condensing onto your thermometer or anything like that. These are just two different temperatures. The dry bulb temperature is just what you think of as temperature. The wet bulb is this crazy temperature that is what you are cooling down to due to evaporation. By the way, it's actually the temperature to which your skin cools when you get out of the shower because, again, it's kind of the same sort of thing. There's evaporation happening off your body instead of off a little wet footie like this. But the idea is very related. Hold on, there it goes. It means that we can get the wet bulb temperature and the dry bulb temperature from this piece of equipment called the Sling psychrometer. And from that, there are tables. There's actually equations too, but in practice we usually use tables. And in like the ATS 114 lab, you're going to use tables. And you read off, okay, for this temperature, at this wet bulb temperature, that's the saturation vapor pressure. That's the vapor pressure, okay? Usually it also has things like relative humidity in it and so on too. All your other ways of describing the amount of water vapor in the air, like relative humidity, dew point, vapor pressure, can all be gotten from tables once you know temperature, T, and wet bulb temperature, TW. Neat. So in practice, this is how it's really done. Now, it isn't always necessarily a person swinging it around. It might be, like some cases, a machine dunks the thermometer in water and then it blows a fan across it. But the basic idea is the same, okay? It's just in a lab situation, we tend to use it where you actually are swinging it around. It's by no means the only way in which we can measure humidity. Another really cool piece of instrument that we use for, and there's a whole bunch of different instruments described in your textbook, but another way in which you can do it is so-called chilled Mir Hydrometer. Let me pause for a second. A hygrometer is another machine that can measure humidity. Psychrometer is a machine that can measure humidity. To be honest, despite the fact that I've done this for decades, I don't actually know why we use the word psychrometer for some situations and hygrometer for others and so on. But another instrument that is commonly used to measure the humidity is the so-called chilled Mir Hydrometer. And this is especially used for like unmanned weather stations where a machine is going to be measuring the humidity. And what you do is you have a mirror with some kind of light shining on it. Often it's actually a laser shining onto the mirror with some kind of camera or light sensor mounted here. And what happens is light from the laser or the light or whatever shines onto that mirror, it reflects off, and the camera can see it, or the sensor can see it. And then, using some kind of piece of equipment, we chill the mirror. And the mirror gets cooler, 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 and at some point the mirror is cold enough that we have reached the dew point. And now, when water vapor molecules hit the mirror, they condense on. The mirror fogs up. Suddenly, the light that is hitting the mirror and reflecting up into that camera or sensor or whatever is dimmed. That exact temperature at which all of a sudden the mirror fogs over is the dew point. This is actually a really good way to measure the dew point. Anytime something like this happens where like condensation forms on the material, you have chilled that material to the dew point. Now when water molecules touch it from water vapor, they condense on. In fact, that's exactly how a glass of water sweats, like in the summer where you get condensation on the outside of a cup. Let me give you an example here with this cup of water right here. You can measure the dew point in the room you are now just with a glass of water and some ice cubes. If you start with a glass of water that's at room temperature, the sides of the glass should be dry. There won't be condensation on it yet. Now put a thermometer in there so you're measuring the temperature of the water. It's going to be whatever room temperature is, 68 degrees Fahrenheit or something like that. Then start adding chunks of ice. Let them melt as they go along. And watch real closely for the outside of the glass. Your temperature is going to be going down and going down. All of this time, water vapor molecules in the air in the room are hitting the sides of your glass. But when they hit the sides of the glass, they're warm enough, they just bounce back off. They're still part of the vapor in the atmosphere. But when you cool the glass down enough by adding enough chunks of ice to it, at some point when water vapor molecules hit the side of the glass, now they cool enough when they touch the outside of the glass that they condense on. You formed dew on the outside of the glass. Therefore, you have now cooled it to the contents of the glass are now cooled to the dew point temperature. So you could do this, in a cafeteria or as a lab activity. Sometimes in ATS 114 we do this and so on. You can just measure the dew point, at least over, well, if the dew point is less than 0 degrees Celsius and so on, you can't get cold enough with the ice and all that, who cares? But the basic idea here works really well. That is what happened. If as soon as the contents of that glass are at the dew point, then when water vapor molecules touch the sides, instead of bouncing off, they condense on, and the glass starts to sweat like that. Pretty cool. Simple little ways to measure humidity. Turns out there's a whole mess of other ones that are really cool. There's a hair hygrometer that uses actual braids of human hair. You probably know that naturally curly hair gets curlier when the more humid it is, and they actually do use human hair in a hair hygrometer to they measure the curliness of the hair as a way of measuring humidity. There's a hygrostor, which is a piece of electronic equipment that uses the electrical resistance across a circuit as a way of measuring the humidity. Your book describes as many of those as you need to know. Okay? Alright, so we have ways that we can measure the humidity, and we have ways that we could describe it. We could quantify it as like a vapor pressure or a relative humidity or a dew point or whatever. Turns out there are other ways that we could do this too. This is going to start looking like quite a list, but there's a reason for it. One of the ways that we're going to be describing the amount of water vapor that's in the air is a number called the mixing ratio, and we'll use the symbol MR for mixing ratio. Mixing ratio is like a recipe for the air that you have. It's just basically how many grams of water vapor there are in the air for every kilogram of dry air that there is in the air. So if in my sample of air in this jar, there's this many kilograms of air that's dry, and then we add this many grams of water vapor into it. It's just a recipe. This comes to us from chemistry. Chemistry often describes mixtures of materials in terms of their mixing ratio. Okay, mixing ratio turns out to be a very useful way to describe the amount of water vapor that's in the air for certain kinds of equations and so on. In practice, we don't use it all that often in this class. I think there's 1 or 2 homework problems where, for some reason, they use mixing ratio instead. Okay, so you have it there. But here's the deal. Just like we had, where'd it go? There it is. Just like there was a saturation vapor pressure that described the vapor pressure when the air is saturated. There is a saturation mixing ratio, SMR, that is the way of how we describe the mixing ratio when the air is saturated. So we could measure the amount of water vapor in the air right now. That's the mixing ratio. Or we could talk about what would the mixing ratio be if the air were saturated. That's the SMR, or saturation mixing ratio. Okay, again, there's just like one or two homework problems, I think, where they get bogged down in mixing ratio. Even less, it's only because they mention in your textbook that I want to mention out, another way we could quantify or describe the amount of water vapor that's in the air is a number called absolute humidity, or AH. The AH, or absolute humidity, is something like the density of water vapor. It is how much water vapor there is, how many kilograms or how many grams of water vapor there is per cubic meter of air, per unit volume. So here's a cubic meter of air, how many grams of water vapor are in it? Okay. Again, it's a very intuitive, makes good sense. Hey, here's a sample of air. I know it has, 1 cubic meter to it. How much water vapor is in there? That can be very useful for certain kind of problems on the homework. It isn't necessarily something we use all that much in meteorology, but I want you to note the pattern here that just like there is a saturation vapor pressure that goes with a vapor pressure, just like there's a saturation mixing ratio that goes with the mixing ratio, there is a saturation absolute humidity that matches up to the absolute humidity. The saturation absolute humidity is the absolute humidity air would have if it were saturated. And in fact, there's a pattern to all of this. Just like we saw relative humidity was the vapor pressure divided by the saturation vapor pressure, and astonishingly also the condensation rate divided by the evaporation rate. That's what CR and ER are here. In the same way, relative humidity is also mixing ratio divided by saturation mixing ratio. It's also absolute humidity divided by saturation absolute humidity. So whatever kind of numbers they give you in a story problem in the homework or whatever, you can always work your way back and figure out the relative humidity as long as you have these other numbers. The Clausius-Clapeyron equation, that graph, can be made, they just do the math, to make it, instead of having the y-axis being saturation vapor pressure, you can make the y-axis saturation mixing ratio, or saturation absolute humidity. And in practice, I think that there is a homework problem that uses something like that. Weirdly, it doesn't work for the ones that are based on temperature. Relative humidity is not the dew point divided by the temperature. You can prove to yourself that that would have to be the case because the temperature could be 0, right? If the temperature was 0, you would have a divided by 0 thing. The saturation vapor pressure, the saturation mixing ratio, the saturation absolute humidity can't be 0. No matter what, if the air were saturated, it would be holding a non-zero amount of water vapor. So you could prove to yourself that that can't possibly work. Why the hell are there so damn many ways of, excuse my French, of measuring the amount of water vapor in the air, or describing the amount of water vapor in the air? Well, this comes to us from the ideal gas law. Remember P equals rho RT, where we were describing the air in terms of pressure and temperature and density? Okay. I don't want to tell you that this is, I don't want you to think like, let's see, if P equals rho RT, then apparently vapor pressure equals absolute humidity times dew point times R. No, it doesn't quite work that way, but it is not a coincidence that it took a pressure-like variable, a density-like variable, and a temperature-like variable to describe the ideal gas law for air, and then it takes a pressure-like variable, namely vapor pressure, a density-like variable, like absolute humidity, and a temperature-like variable, like dew point, to describe the water vapor that's in the air. It's not a coincidence that it takes these three numbers, but it's not a simple thing how those three things are related. But the idea is a solid one, that it takes those three different ways to describe it, to describe the amount of water vapor that's in the air. Now, just to review, originally we're going to have all the stuff about like how do we get clouds and how do we get condensation and all that. No, we moved that to a later lecture. But just in this lecture, what we reviewed is it turns out there's a whole lot of different ways to express the amount of water vapor that's actually in the air, like vapor pressure, or absolute humidity, or mixing ratio, or dew point. All of those are dependent on the amount of water vapor actually in the air at the present time. Turned out there were lots of different instruments for measuring the amount of water vapor at the given time too. We focused on chilled Mir Hydrometer and on Sling psychrometer, but you'll find other examples in your book as well. Then, we talked about the fact that you could bring air closer to saturation, in other words, increase its relative humidity, or you could bring air farther from being saturated, in other words, decrease its relative humidity, by either changing the amount of moisture that's actually in the air, but that was sort of the hard way to do it, or by changing the temperature of the air, which is in practice what's going to happen in the next lecture. Okay. But, before we get there, let's answer 3 quick questions and take a break. Question 7. On a Sling psychrometer, that's that instrument where you swing around like this, the temperature recorded on the wet bulb is the A, temperature of the air itself, B, the dew point of the air, C, the vapor pressure of the air, or D, trick question, none of these. What is measured by the wet bulb, the one with the little wet sock on the end of it? Make a choice from those 4 options and get some feedback before you move on to question 8.